Hello and welcome back to our survey of plasma physics course. We are now at lecture 21, and we only have a few more lectures left, and we're going to try to learn a lot more interesting things. We're going to pick up from where we left in the previous lecture, which, as you will remember, was waves in a cold, uniform magnetized plasma. Let me put a box around that. What we were working on was to write the relation J equal to sigma, where sigma is a tensor, dot E in Fourier space. And the expression that we found defining omega cyclotron species minus omega squared to be equal to 1 over lambda, just for convenience. We found the system of equations, Jx, Jy. I'm not going to say Fourier, but this is all in Fourier space, and you have this from the previous lecture. So I'm going to go a little quickly because there is nothing new here, and I don't need to redefine any quantities. Remember that when I have a subscript 0, I mean an equilibrium quantity, unperturbed quantity. If there is no subscript, I'm implying a subscript 1, which means this is a perturbed quantity. Here we have minus, exactly, let's do it again, minus I omega times lambda, so divided by this quantity I have up here. And the next one was cyclotron species times lambda, and here I have 0, and here I have 0. Remember that minus I omega lambda, the determinant diagonal is the same. This is the same term, but with the opposite sign, and we have zeros here, and just I over omega here. So this is our tensor sigma, and this multiplies Ex, Ey, Ez. And I was saying, remember that the magnetic field is in the Z direction by assumption or by definition. Okay, so that's where we were. Question is, where are we going? It's an excellent question. Well, first of all, we have defined the conductivity tensor sigma. Then looking back at the equations we wrote in the previous lectures, we can also define the electric tensor capital K, that's equal to the identity tensor minus, let's see, how do I want to write it? 1 over I omega epsilon naught sigma. Okay. And that I can, will you remember that this is the dielectric tensor, hopefully. Well, let me just remind you. So let me write it down explicitly. Dielectric tensor. And based on the information that we already have, it's easy to express the dielectric tensor. I'm going to skip a step and do it the way the textbook does. And I'm then going to define the various quantities that appear in the expression I'm going to write now. Okay, in the top left, I have a quantity S, then I have minus ID. The zeros remain zeros. And here I have S again, and here I have minus ID, 0, P, and 0. And oops, I copied this from the textbook, but this sign should be a plus, not a minus. Just stop for a moment to go back and look at my notes. You can see it from up here in the definition of sigma, they have opposite signs for the terms 2, 1 and 1, 2, or if you prefer x, y, and y, z. And the I doesn't change anything, doesn't change those terms. So those terms should still have opposite signs. So be careful with that typo in the textbook. Unfortunately, I like our textbook, but it's got a few typos here and there. Okay, let me now define what these quantities are. And these are defined as follows with a pen. S is going to be equal to 1/2 of R plus L, and D is going to be equal to 1/2 of R minus L, which is, I think, extremely informative. In fact, maybe actually smarter to write it this way. Sorry about that. D is 1/2 of R minus L, or 1 minus the sum over S of omega P S squared. Omega P is omega plasma. I'm hoping and assuming that you will not get confused by symbols. If you do, well, go back to the previous lectures and find them, and good hunting. While D is just going to be equal to the sum over S of the same quantity, omega PS, over omega square minus omega cyclotron square. Did I miss something? Yes, I made a mess. Sorry. This is square, and this multiplies omega cyclotron, and here the whole thing multiplies omega. Let me just make sure that I have this right. I think so. Okay. Now I'm using the standard names for these quantities, and here's where they come from. This is a sum, R plus L, and this is a difference, R minus L. A legitimate question that I would expect some of you to ask is what are R and L? Well, you can get them from S and D. That's kind of silly. But they also have their physical meaning. Now, before I get there, let me just complete the set of definitions by including the term P, the one I have in the Z component. And that's going to be 1 minus the sum over S of omega PS square over omega squared. And that should hopefully be right without any further issues. Now, R and L. Those are defined as follows. R is 1 minus the sum over S of omega PS squared divided by omega times omega minus, I'm sorry, plus this is the right one. Okay, I gave it away. R stands for right and L stands for left. And let me finish writing the expressions. Now, here I have omega, omega minus omega CS. And these expressions come out sort of naturally by doing the derivation using in terms of polarization. And in fact, the R term is associated with right-hand polarized mode, and the L term is associated with a left-hand polarized mode. And also, as a reminder, the omega cyclotron has a sign. There is that's not the absolute value, it's the value with sign. Confused yet? Well, there is I think a good point to pause and stress the fact that this is a pretty simple case. We have a straight magnetic field that we set to be in one direction, and that's it. There is nothing else. Straight constant magnetic field. There is nothing else going on in our plasma, and this is already getting pretty messy. That is to say, the study of waves in magnetized plasmas is not topic for soft-hearted people. There is a lot that goes on in here. And in fact, the way this proceeds is actually to use the to write the dispersion relation in terms of the index of refraction instead of the wave number, which you may think will introduce more confusion, even that is a legitimate legitimate worry, but that is the way these things are normally done. I've seen this done pretty much in the same way in multiple textbooks. I think everybody is taking from sticks. Was the go-to reference textbook for plasma waves, and the way it's done there is the way that's gone into the tradition of how we're going to write this. Okay, now we're going to work, as I said, in terms of the index of refraction. And what we want to do is, sorry, take our dispersion relation. Remember, this is a homogeneous case. That is our dispersion relation for the homogeneous case, which, as we have it from our textbook, looks like this. Let's see, n cross E plus, and this is in Fourier space, I should emphasize, plus k dot E equals 0. And we're going to work on this expression and see where we end up. So just in case, let's see. I don't think you need to me to remind you, but n is c over omega times k. Okay, so knowing that, we can write our monster of metrics. We can at least simplify things a little by picking the direction of our axis. We said that the z-axis is aligned with the magnetic field. We haven't said anything about x and y. And that means that we have the freedom to pick the directions of the x and y axes. And what we're going to do is set the axis so that let me do it this way. Y is equal to 0. Which implies that n is equal to nx, 0, and z. Or we can define an angle, theta, which is not the poloidal angle, such that n sub x is n times sine of theta, and n sub z is n times cosine of theta. Can always do that. This is completely general. All I'm doing is picking my axis to make the problem a little less messy, but it's still going to be messy enough. I'm not going to do all the steps. The next step is to write down, we have the expression for k up here. We write down n cross e as a matrix times e. That's pretty straightforward to do. And then we put all the pieces together. I encourage you to try do the algebra. There is nothing particularly conceptual about it. It's a lot of bookkeeping. We have to be careful about not losing any terms, but there isn't anything terribly profound. It's really just a matter of not messing up the calculation. Okay. And dispersion with erratic spelling. We can obtain the dispersion relation from the general matrix form of our expression, our equation, which is going to look as follows. All right, let's do it. Or not. Just throw my pen. Hold on. Let me see if I can find a pause. Okay, finally, here we go. It's going to look like s minus n squared cosine square of theta. Here we have minus id. Here we have plus id. S minus n squared. Then the cross term is n squared sine theta cos theta in symmetrical positions. And a couple of zeros, fortunately, and then p minus n squared sine square of theta. The whole thing multiplies e transformed and this must be equal to 0. You know how to do this, of course. We set the determinant to 0. And that's going to give us an expression of this kind. We're going to get an expression into the fourth. Actually, you may expect an n to the sixth term, but if you work this out, you'll see that the n to the sixth terms actually cancel out. And that's why it the determinant only has a fourth order polynomial in n. In fact, it's even better than a fourth order. It's a second order polynomial in n squared. And it looks like a times n to the fourth minus b times n squared plus PRL equal to 0, where everything has been defined earlier. And so you just go and look at those definitions. And just for completeness, when we write PRL, we often mean physical review letters. That's not what we mean here. But it's the product of the term P times R times L. We've defined all of those above. All right, almost there. The solution, well, just calculate n squared. It's going to be equal to B plus or minus F divided by 2A, where F is another mass. That looks like this. You can easily do this by hand if you have time to kill. You can easily put this in mathematics if you have a little less time to kill. Again, there is nothing conceptually terribly challenging here. It's just a matter of walking through the steps and working out the details of the calculation. A bit of algebra, but that's what we get. And I should also mention, let's see, let me type this. For historical reasons, this is often, or at least sometimes, written in what's called the well, let me write it this way. Oops, that didn't work. I just wanted to copy and paste, but from my other reference, this is called the next one I'm going to write is called the Appleton-Hartree dispersion relation, and that's written as n squared is equal to 1 minus 2a minus b plus c divided by 2a so there minus b plus or minus f, where c is PRL. So usually f squared is positive, which means that n squared is real. And that's going to give us either a propagating or an evanescent wave in this model. Now, one more way to write this system, when people didn't have Mathematica, worked out everything by hand, and different people worked out things in different ways, which can all be correct. So here is our next one, next and last. Square tangent of theta is going to be equal to minus p times n squared minus not plus, sorry about that. N squared minus r times n squared minus l, 1 minus r times n squared minus l divided by s times n squared minus r l multiplying n squared minus p. Okay, now there are going to be sorry about that, and some special cases that are going to hopefully help us a little bit. Let me just go back and make sure that I didn't do what I think I did. Yes, I thought I did. I didn't define what A and B are. Oops. Well, so let's get us some space and put them back in. A is S times sine square of theta plus P times cosine square. So much. Theta, and B is RL sine square of theta plus PS times 1 plus cosine square of theta. Now, each one of the expressions I'm going to square now is our dispersion relation with all the necessary definitions being implied. Now, the tangent form of the dispersion relation also allows us to easily identify some special cases. And those are going to be given by theta equals 0. which is a case where p is 0, n square is either equal to r or n square is equal to, oh, sorry, change notation. We're using lowercase n, or n square is equal to L. And the other obvious limiting case is theta equal pi over 2, where n square is equal to RL over S, or n square is equal to P. I hope it's clear what I've done. I've said in the first case, the numerator equal to 0, and there are three values, three options for making that equal to 0, either P is 0, or n square is equal to R, or n square is equal to L. In the second case, as said, theta equal pi over 2, it gives me an infinite tangent. And to get that, I need the denominator to be 0, and that's given by n square is equal to RL over S, or n square is equal to P. And physically, these two cases correspond to the parallel and perpendicular case, where parallel and perpendicular refers to the magnetic field, the direction of the magnetic field, and the and the index of diffraction or wave number. Okay, so there is going to be a good number of special cases. We could pretty much spend the rest of our course just examining this dispersion relation. Well, maybe not the rest of the course, but at least 3 or 4 more lectures. That's again to emphasize that waves, even in a cold plasma with a straight, uniform, and constant magnetic field, they can be pretty messy. What I'm going to do is just look at the first case that's in our textbook, which corresponds to parallel propagation. That's already going to give us a good number of concepts and help us learn a little more about waves already. And hopefully that will be enough for you to go and learn about different types, or put them in a homework or project if needed when that arises. Okay, so let's look at the parallel propagation case. Parallel propagation. Remember that this corresponds to theta equals 0, as we just said. And we have three different routes that I just wrote, and you can see just above here. Now, what may be instructive is to rewrite the equation, the dispersion relation that we have here, in the special case where theta is equal to 0, well, of course, the sine is equal to 0 and the cosine is equal to 1. Let's see what that looks like. Then I'm perhaps doing a slight abuse of notation by calling this a dispersion relation, since a dispersion relation is typically more properly or strictly meant to represent an equation for that relates the wave number and the frequency, or the angular frequency, or the index of refraction instead of the wave number. But often, especially here in plasma physics dealing with this type of waves, we call the dispersion we also call dispersion relation the matrix equation that relates sort of that gives us the equation for the three components of, in general, the electric field. That's the standard, most reasonable way to do it, but in principle, you could do the same thing for the magnetic field, the perturbed magnetic field. Not perhaps for all waves, but at least for some. Okay, enough delaying. Let's see what our dispersion relation looks like. It's going to look like this: s square minus n square. Then we have minus id, we have plus id. Same term here, s square minus n square. Here in the ZZ piece, we only have P, and the rest of the terms is 0 because they have signs, or they were 0 to start with. And this multiplies EX, EY, and EZ. Okay, then. We can look at the roots one by one. And the first easiest one is the case where P equals 0. Well, this is easy. This implies that E is 0, 0, EZ, or let's see, the book is using E0. And I'm dropping the subscript F for the Fourier transform. Remember, Fourier transform is a linear operator. So if, well, not only it's a linear operator, but it operates on components separately. Well, maybe that's part of being a linear operator, but regardless, in that case, where P is equal to 0, only the Z component of the Fourier transform of the electric field is non-zero. And when I've transformed it back, I'm only going to get the Z component of the electric field. And for that reason, I can just write my answer to have this form in terms of the electric field in physical space rather than in Fourier space. Now, again, this is something you can work out by hand or by Mathematica or whatever else you like to use relatively quickly, but I don't think it's worth the time to do it in a lecture. I'm just going to state the results and try to comment on what they can tell us. Okay, second and third case, they're similar. Now I'm going to write the answer as the book does in terms of the Fourier transform. And this is going to be E0 plus or minus, it's plus I E0 and E0. And the third case is analogous, just with a minus sign for the imaginary piece for the y component. And in this case, n squared is equal to L, and therefore E, there is a missing equal sign here, E is going to be equal to E0 minus I E0 and E0. Okay. So now let's see if we can find any more information from what I just wrote. Not sure we'll manage to go through all I would like to say in the time we have left, but let's try. Let's start from the first root. Well, that gives us an electric field that's parallel to the z-axis, and that is the direction of the magnetic field. It's also the direction of K. And these roots is a longitudinal wave. And you may recognize it. It's the same wave we found for called unmagnetized plasma. And the reason is that in this case, the particles oscillate along the magnetic field, and therefore there is no V cross B term in the equation, the equation of motion. And again, going back to what we've seen for the unmagnetized case, this oscillation occurs at a frequency equal to the plasma frequency. Up to you to decide how profound what we did was. We may have spent a lot of time to find a wave that was we had already found doing a simpler calculation, but everything was notwithstanding the skipped steps and rigorous, there was no hand waving. There's a ton of algebra, and I don't know of anyone that works it out in detail in class. I'm sure there will be somebody, but I think that most people will just state the results. But this would be a great exercise to do in your own time, because you may have to work on similar problems, and having worked it out once, at least by hand, Mathematica is not always the answer, will sort of stretch your mental muscles for this type of calculation. Now, we see that in the second and third root, the we have electric fields that are perpendicular to the magnetic field in the direction of propagation. So that means that these are transverse waves. And in fact, what we also observe is that these waves are, again, phases or roots. Different from the first one, these ones are electromagnetic. That means that B is non-zero. Not the equilibrium, there is no subscript. So that's the the perturb B. And the way to see it is by observing that using Faraday's law, taking the curl of E, oops, sorry, I got an extra I. There is an I that comes from the time derivative of B. It gives me 1 over omega K cross E transformed. K is in the Z direction. E has an X and Y component. Therefore, that cross product is non-zero. Okay, as for charges, let's see what Gauss's law. Oops, sorry. Before I do that, let me fix a typo here. That's my bad. These are zeros. P is non-zero, so I need the Z component of the vector field to be zero in these cases. Okay, now back to Gauss's law. You see again and again the advantage of working in Fourier space. The perturbed charge density is going to be given by epsilon 0, divergence, which turns into an I K dot E, and this is 0. K is in the Z direction, and D does not, contrary to what I wrote earlier, have a Z component. Now, the last thing I wanted to point out is the meaning of left and right polarization. Well, you know what left and right polarization are probably better than I do if you've been TAing for 1610 and since you just took E and then. in at the graduate level. But let's see that these terms really, these quantities R and L really correspond to right and left polarized waves. And the way this goes is the following. We have, let's examine this case 2. And the other one is completely analogous. Now, in this case, n squared is equal to R. And as I'm not going to do it, minus n squared is, okay, I don't know what happened to my technical problems. The joy and beauty of, okay, you can see my screen again. Very good. All right. Okay, s minus n squared is equal to minus R minus L over 2. That's equal to minus D for the, when the other case is easier. Maybe I can write them both. Oh no. Sorry about that. Let me write it here. Maybe I took even too much space. Yeah. In case 3, we have n squared equal L, and s minus n squared is equal to plus D. So the point that I'm trying to make following the discussion in our textbook is that the only difference between the two modes is the sign of the y component. And the I in the y component indicates a shift of 90 degrees. And the sign is going to tell us it's a shift plus or minus pi over 2. That's really all there is to it. So in the right polarized case, the case 2, the x component in real space is going to be the real part of E0 e to the minus I omega t. And that gives me a cosine. And EY is going to be equal to the real part of I E0, getting from the eigenvector here, times e to the minus I omega t. And that gives me a sign with a plus sign. E0 sine of omega t. While in this case, I'm going to have the Ex is the same. That corresponds to E0 cosine of omega t. And Ey is going to be almost the same, but I have a minus sign. So it's going to be minus I E0 e to the minus I omega t. Then I go take the real part and I get minus E0 sine of omega t. So really, the first one, the one that's on the left, is, I didn't do that very cleverly. Right? The one that's on the left is the right polarized wave. The one, the other one, the case 3, is the left polarized wave. This turns to the right. the right polarized wave turns to the right, and the left polarized wave turns to the left, as they showed. I still wanted to get into frequency dependence, but that's going to take another little bit of work. So I know this is a lot. You may have to go through your textbook carefully, and I don't know if what we said here helps. I hope so. You may have to listen to it more than once. But the main messages before we close for today are, well, this is complicated. Even for the simplest case, there is no way around it. It's complicated. And a lot of the complication comes from the algebra. It's just a lot of algebra. In other words, this is what I would call a complicated problem that is not actually difficult. It's everything is straightforward. It just takes a lot of work. It's like walking 10 miles. It's not, there is nothing conceptually difficult, but it's a lot of work. Okay, we'll look a little more about frequency in the next lecture, and then we'll move forward with remaining topics. Thank you, and I will see you for lecture 22.